Let's say we're looking for Animaniacs. Hit search, and it found Animaniacs. Welcome back to Arcade. I am Super Tommy, and in this video, we're going to look at another algorithm, the binary search algorithm. Now, this is a very popular search algorithm because it is so fast, as long as you can sort your list ahead of time. So, binary search, as shown here in this Wikipedia article, is also known as the half-interval search, the logarithmic search, or binary chop. That's probably my favorite name of it that no one I've ever heard use. But basically what binary search does is given a sorted list. So for example, we have this list of Super Nintendo games. This is a list of 1,800 games. And it's sorted alphabetically from numbers to A through Z. And what the algorithm does is, given a sorted list, it'll check the middle and then see if the thing you're looking for is less than or greater than the item in the middle. Now, if it's less than, it's going to now discard the second half of the list and then only look at the first half. So now you've deleted half of your search, half of the number of items you need to search. Now from there, it does half again. So it's going to pick the middle of the original half of the list and then check if the thing you're looking for is less than or greater than the thing in the middle. And now if it's less than or greater than, whichever it is, it'll discard the other half. So now you have a quarter of the list. It's going to do it again, and it'll discard half, and then now you have an eighth of a list. So eventually you'll get to, by deleting half each time, find the item you're looking for eventually. So you'll see in our example that basically anything can be found within 11 searches. So the alternative to doing binary search, if you had a sorted list, is quick sort or merge sort or some other, not sort, that's those sorts, is to look for the thing from the beginning to the end. You can use quick sort or merge sort to sort your list. But if you're not using binary search, you can look from the beginning of the list to the end of the list until you find the thing you're looking for. So in the case of this 1,800 item list, you would start from index 0, and if what you're looking for is, for example, at index 1,400, you would have to look 1,400 times to find your item. Now, of course, if the thing you're looking for is at index 0, then you will be faster than binary search. But that is only going to be the case up until, perhaps in this case, this is a 1,800 item list. If the thing is within the first 10 items of the list, it'll be faster than binary search, but you can predict that. So binary search would perform better in like 90 some odd percent of all cases, and in general it would perform better, so that's why you would use it. So let's implement binary search in JavaScript here, and we'll show it to you by putting a name here, hitting search, and then we'll animate this search for you so you can see how binary search works. So we're going to base it on this pseudocode from Wikipedia. Here is the pseudocode that they have, which is only in 6 steps. So let's see how that translates into JavaScript code. So we have this function here called search. Now it's going to take in a name. That is going to be this value here. So we've set up this demo web page relatively simply. This is just divs with divs inside, and then it can scroll. So you don't have to really worry too much about how this setup works. We have this list of elements. That's what we're going to be searching. So the elements is each div that we've created based on this list of Super Nintendo games. Okay, so let's start. Let's delete this to do. So what should we do first? Pseudocode. So it's to set L to 0 and then R to -1. So I don't really want to use L and R because, I mean, it means something. It means left and right. So we're going to use slightly different terminology. We're going to go with let, because we're going to be changing these values. So let start. So start is the beginning index that we're going to start as the range. So given our 1800 item array, the start index is going to be 0. The end index is going to be, end is elements dot length minus 1. Should I do minus 1? What does this say? Yes, okay. End minus 1. Now, we want to, what does this say? So if L, yeah, we'll do that later. So now we want to get the middle. So this is binary search. We're going to cut it in half and check the middle. So let's see, what should I call it? Middle. Well, yes, we will call it middle index. But what we're going to do is also have a thing to, the place to put the thing we find. So we're going to call that item. It's going to be undefined. Ooh. Item. It'll stay undefined. And we're going to do this search until an item is found or until this L greater than R, or in our case, start is greater than end condition happens. So let's just do that. So while item is undefined, we're going to perform logic. We're going to perform the binary search logic of going to the middle, comparing left, right, going to the half that the item I'm looking for should be in, comparing from the middle, comparing left, right. Okay, so there we go. So now we want to know, let's call this range. So this range is going to be end minus start. So because start can change and end can change, we need to get the number of items that we're going to be looking at. So at the very beginning, it's going to be, end here is 1800 minus 0, so range is the entire length of the array, right? So just bear with me here, you'll see. So let's see, middle, which is going to be start, right, plus, so we're going to do math.floor, range divided by 2. So to get the middle, we're going to do range divided by 2. So in this case, at 1800, where start is 0, end is 1800, roughly, the middle is 900. And we're adding start here to start because start could also be in the middle. So for example, if we continued here and we found that the item we're looking for, which is name, is on the second half of the list, we will want start to be the middle number, right? It'll be 900 to 1800. And then our range is going to be that 900, but starting at start, which is 900. So then when we get the index, which is middle, it'll correspond with the second half of the list opposed to the beginning of the list if we did not add start and if start wasn't 0. So let's just do it so you can see. So let's see here. So this is the element we're going to get out of elements, middle. So this is going to be the HTML element here, this div, the div that we've selected as being the middle of the array. And then we are going to get the actual name or the value out of it. So we'll just call this value elem.innerText. So this is actually like right here, it says Acme Animation Factory. That is what elem.innerText is, and we're going to put it into value. Now we're going to compare that. All right, so let's go back to our pseudocode. Okay. Right. So if am, so in the list at index m is less than t, set L to m plus 1, go to step 2. If the reverse, I guess, if a at index m is greater than t, set R to m minus 1. Now, if a at index m is equal to t, we found what we're looking for. Now, I personally don't like reading this mathematical notation, even this is a bit too much for me. Here's what we're going to do. We're going to base ourselves on the pseudocode, but let's just do with the obvious. So if value equals name, right? So obviously if they are the same, and in fact, we should lowercase this. Lowercase, because in JavaScript, we can compare strings using less than or equals, less than or greater than, and it'll work as long as the strings are in the same case. So we're going to do lowercase. So if value equals name, and also it makes us compare better. So if you're typing in capitals or you're typing in lowercase and there are capitals, it'll work still. So if value equals name, that means we found it, so we can exit out of this while loop. So let's just set item to elem, right? Simple. If for some reason the middle one is the correct one, we found it, fantastic. Now, if value, let's do if name, so the thing we're looking for is less than value. So now that means we're in the first half of the list, which the algorithm says if it's less than L, right? So if less than T, so if the value here is less than T, set last. So we're going to do the reverse. Basically, we're going to set start to middle minus 1. No, is that right? No, it's on the second half. So end is equal to middle minus 1. Yes, and then else if name is greater than value. So now if what we're looking for is on the right side of the list, we're going to set start to be middle plus 1. So now we're doing minus 1 and plus 1 because we've already checked middle and it is not middle, right? So we already looked at the element at index middle and it is not equal to the thing we're looking for. So we can just do minus 1 if we're going left and plus 1 if we're going right. So there's that, fantastic. So now we do that, we come back into this while loop. Item is still undefined because we haven't found it. Then we do this math again, which is end minus start. So let's just say it's in the left half. So now end is 899, let's say, and start is 0. We do this subtraction, you've got 899. So 0 plus 899 divided by 2 is something. We do the middle thing. We get the element at middle. Then we do lowercase. We do this check. Is this found or not? If it's not found, keep doing what we did before. So now we're going to cut that smaller half list into half of itself, or what was a quarter of what it was before. Okay, so that looks pretty good. Now our method here has to, our function here has to return an item and the compares count. So this is when we log it out in the constant, you see how many checks we had to do to find what we're looking for. So let compares count equals 0. This is just for us to see how binary search is working. And so basically every time we come in here, we're going to increment compares count, and then let's just return item compares count. So this will be used down here. So we're calling search here. Then we're just going to log out how many checks we did, the item we found, and then we will scroll to it and highlight what we found. Fairly simple. Now, this could work, and you probably, let's just try it, right? I think this will work. You just won't see it animated all the way, but that's okay. Let's say we're looking for Animaniacs. Hit search. And it found Animaniacs. And it did it in 11 checks, and that's the thing it found. So now let's just see it in action slower. But so basically, this is binary search. We've implemented binary search. It only took us about 13 minutes. And here it is. This is the full binary search right here. I mean, you gotta declare your variables, do this while, and there's your binary search. The item is found and is returned. So this is an async function, so we can slow it down and highlight things as it checks it to watch it do its thing. So let's see here. So we have these utility functions here from util that we've already made. So first, let's scroll to whatever element we find. Container is this elem. We're going to scroll to there, and then we're going to add a highlight. So we're just going to just highlight the row here. We're going to highlight the elem, and then let's see. Then we need to wait. Wait for seconds. Let's wait 1.5 seconds. 1.25 seconds. And then we are going to remove highlight. It's pretty good. Let's look for Animaniacs again. Animaniacs. Search. That's the middle. That's the other half. That's the other quarter. Now, of course, I lost count. But you see it just going half at a time. And there we go. And it found Animaniacs again in the 11 checks, just like it did before, without this animation to show you what it's doing. So let's see what it does. Let's just pick something else, right? So that we can see how it would work for something. Let's say the last. Let's say the last one. I'm not actually sure what this is. Let's just look for Zoop, right? So if you were doing a linear search, one at a time, doing like array dot find, right? For example, if you can I do this here? Let's say item is elements dot find, right? So this is the built-in find method of array. You probably used it before. Element, the elem, right? So you would do return elem dot intertext dot two lowercase equals name, and then that will be the item. And so let's just do that. I think we can do this. Let compares count 0 plus plus compares count. So let's say we did a linear search. This is the slowest possible search. And let's just do it for Animaniacs. Let's see what this does. That took 44 items checked, so that is at least 4 times slower. Now, if we looked for Zoop, it checked 1,807 items, right? So now you couldn't tell that the computer had problems because it didn't. It's only 2,000 items, which is nothing. But if for some reason you had like a million items or 10 million, 100 billion, 4 trillion items, whatever, that's probably too big. 4 billion items, whatever it is, a very large array, and you had to do it quickly. You can't just block the computer. So you may have seen when using websites or software yourself that sometimes you'll click on a button and then it sort of freezes and then it continues. So there could be many reasons for this, but in some cases we could be doing a search that's taking a very long time because you're searching, either it's a network call and then the server is doing something and it's coming back and your network's a little bit slow, or if it's happening locally, it's searching through a very long list and that's going to take like a second, maybe half a second. But that even small amount of time, half a second, not really that small, but especially for games, that would be way too long. That kind of delay is not very. It's poor experience because you don't get that feedback immediately. That's why you want to use something like binary search. So since this took 1,807 checks to find the item at the end of the list, this is the worst case scenario for a linear search. So instead, let's try this now with binary search, and we'll see how many compares it takes to find the last item in the list. So this was Zoop search. Middle, it's going to do the whole animation thing to show you what it's doing and how it's going to find what it needs to find. And boom. That was 10 items checked. So I don't know, was that 180 times faster than a linear search, right? I think so, yep. Yeah, I think that's probably right. 180 times faster than linear search. So now that is binary search, and it is pretty simple. It's just right here. You don't really need this compares count. We've added some things so that we can see the performance versus a linear search. So now, when we talk about search algorithms and algorithms in general, you'll come across something known as big O notation, and that is the time complexity of an algorithm. Now, binary search, as you see here, worst, best, average, and worst case space complexity. So space complexity we're not really talking about, but in binary search it should be basically nothing. This is constant, since we're not creating new arrays, so space is in memory. For binary search, what we care about is time complexity, or which is log n. So it's logarithmic, which is one of these nicknames it has. But what does logarithmic time mean? So let's just go here. I think they do have some charts, but I don't know how much that helps you. If you're a math person, they may help you. But let's look at this list here. So they have a list from O(n), which is constant, which is as fast as it can be, all the way out here to O of n factorial, which is the slowest it could possibly be. If you remember factorial, it's I think it's 1, or if it's 5 factorial, 5 times 4 times 3 times 2 times 1. So it's just gets massively large. And then there's O of n squared. there is O of n cubed or n to the fourth or whatever. So the further you go down this list, the slower your algorithm is. So you want to be as close to this part of the list as you can if there's an algorithm that does what you need. Sometimes you have to use slow algorithms because there is no other way. There's only a brute force method available. So binary search is O of log n. So this is, I don't know what log n is. I'm not even sure how you would visually think about log n. But basically, it's one of the fastest algorithms you could do. It is O of log n. So anything further up this list, good. Anything down this list, not as good. But if you have to use it, then that's what you'll have to use. So that is the time complexity in big O notation for binary search. Now that is all for this video. If you liked what you saw, please do subscribe. And if there are other algorithms you would like to see, do let us know in the comments below.